Now let's talk about what's called the first derivative test. So underpinning this video and the next is the question. Question: if C is a critical point for f at x, is it a local maximum or minimum? So how have we answered this question thus far? Thus far, we've answered this question by finding some critical points, plugging in some values, and seeing which is the biggest and which is the smallest. Don't get me wrong, this does work, so long as we can compute those numbers effectively. But even though that works in a lot of cases, that doesn't mean we might want to be able to do a little bit better. So let me state what's known as the first derivative test, and then we'll talk about it. So the first derivative test says the following. So, fact, let C be a critical point of f at x. So then, if f prime at x is greater than 0 for x near and less than c, and f prime of x is less than 0 for x near and greater than c, then C is a local maximum. All right, so I don't want to write all of this out again just for time, but if we have sort of the same statement, if, well, you have the same thing is true, but it starts off negative before C, and then it ends off positive after C, then C is a local minimum. And finally, if f prime of x has the same sign on either side of C, then C is not a local extremum. All right, this is a lot of words. Let's draw some pictures to talk about how this works. So, let's draw out a picture of a local maximum. Well, it's going to look something like this. And what happens? Well, C is a critical point. Before C, we see that the derivative of this function is going to be positive. It's going to go positive, positive, positive before C, and then it's going to start being negative. So indeed, that is what this first bullet point is saying. It's saying that if you have a function where the derivative starts off positive before C and then is negative after C, that's going to give you a maximum. And indeed, we can continue the function on. Maybe the derivative doesn't stay negative, maybe it starts being positive again later, but we only need it to be negative right after C and positive right before C to make this conclusion. What it does far away from C isn't relevant to us. Similarly, for the second bullet point, we could switch this around and we see a very similar picture. Shows us that, okay, if we have a local minimum here, right before C, we have that the derivative is negative, and after which the derivative is positive. Indeed, if you have a local minimum here, the function starts slowing down beforehand, but still the derivative is going to be negative, and then it's going to start speeding up afterwards. Okay. Finally, for the final case, you could have a function that looks something like this. You could have a function where, even though you have a critical point maybe you have a function sort of like this, where the derivative is positive before and after your critical point C. We can see pretty clearly from the picture, and we also know from previous videos, that if the derivative is positive here and positive here, the function is going to be increasing on this whole range. But what you can do is you can refer specifically to this fact, which is called the first derivative test, in this case to show that C, even though, for example, maybe its derivative is 0, it isn't a local maximum or minimum of the function because the derivative is the same side on either side of C. And we can, of course, flip this picture around where the derivative was negative on either side. So that's how the first derivative test works, and here are a bunch of basic pictures, but now let's dig our teeth into some actual examples that aren't just pictures. Alright, so an example which is coming up a lot is f at x, which is equal to x cubed. So we can see that f prime of x is equal to 3x squared. So notably, we have that f prime of 0 is equal to 0. But this 0 is not going to be a local maximum or a local minimum for x cubed. If we draw the graph out, we see that it looks something like this. And 0 from the picture clearly isn't a local maximum or a local minimum. But note what happens. We have that f prime x is greater than 0 for x greater than 0, and f prime at x is also greater than 0 for x less than 0. Because this function here, f prime at x, 3x squared, if x isn't 0, it's always otherwise positive. So indeed, we can use the first derivative test to conclude that 0 isn't a local extremum of this function because the derivative is the same sign on either side of the critical point. So we like the first derivative test when it finds maxima and minima for us, but we also even like it when it shows us when points aren't maxima or minima, which it does here. So that's one example of this test in action. So another thing we could do a slightly more complicated example. Let's go back to this function, this f at x is equal to this guy here. Okay, and again, the graph of this one looks something like this. So we can see from the picture where it's increasing or decreasing, but let's just go through the process, if you had never seen this example before, how you would do this. So again, what we can do is we can say f prime at x is equal to, and I'm only going fast because I've done this example before, but we know that on this region here from minus infinity to minus 2 and 1 to infinity, we know that this guy on the inside is positive, so the derivative is just 2x plus 1, and this is either when x is less than minus 2 or x is greater than 1, and in the middle, when we have x between minus 2 and 1, that our derivative is minus 2x minus 1, and we know that we have critical points at, well, minus 2, 1, and minus 1/2, which is this guy here. Alright, and we can even know that these guys here are minima and maxima respectively, but what's interesting about this is we don't need differentiability at critical points to use the first derivative test, because I won't do all three of them. Let's just do this point 1 here, and let's show that 1 is a minimum rather. So why is 1 a minimum? So note, at x is equal to 1, we have that f prime of x is less than 0 for minus 1/2 is less than x is less than 1. That's something that we talked about before. If you just take this guy here and you plug in numbers between minus 1/2 and 1, you're going to get a negative number here. And f prime of x is greater than 0 for x is bigger than 1. That's just unilaterally true. You're in this range, and if you plug in a number 1 or greater into here, you get a positive number. So indeed, this 1 is a critical point because it's not even differentiable at 1, but that's fine. The first derivative test actually doesn't even care about that. We still see that the derivative is negative before 1 and positive after, and that still allows us to conclude that 1 is a local minimum. Now, you might say, well, we already knew that 1 was a local minimum for this function for a number of reasons, but of course, I think we can note that though we already know how that works for this function, there are lots of other functions where this might be very useful for, where if you have a nasty critical point that's at a point of non-differentiability, it's extremely useful that the first derivative test can still be made to apply.